Good morning, everyone. My name is Luoping Zhang, and I'm from Wake Forest University. And today, Jack and I will talk about our topics, doing work with Script Ballard, accelerating neural network training using arbitrary precision approximating matrix multiplication algorithms. In our project, we curate practical, approximate, and fast matrix multiplication algorithms. And we also generate efficient multi-threaded code for all of them, and they provide 25% improvement. And we also show neural network training is robust toward the error produced by the approximate algorithms. And lastly, we accelerate the multi-threaded training performance of different neural network models up to 15%. As we all know, neural network has a lot of applications, but it has its problem, which is it takes a long time to train. So to improve their performance on training, we believe that if we can speed up the time spent on one of its bottlenecks, which is the matrix multiplications, then we can get it done much faster. So when we are doing matrix multiplications, we are usually using the classic algorithm. And this algorithm has 8 multiplications for each recursive step, and its complexity is in cube. And Strassen find a faster algorithm shown below here. And this looks complicated, but it only have 7 multiplications. So if we want to compute its complexity, it's exponent of n equals to log base 2 of 7 multiplications, which equals to 2.81. And this means that this algorithm is much faster than classic algorithm. But however, it is not likely to find a 6 multiplication algorithm. So another way we can do is to change the matrix dimension, or how we divide these matrices. So for classic and Strassen algorithm, they both work on a 2x2 and 2x2 submatrices. But years later, Bini found out another algorithm. It works on 3x2 and 2x2 submatrices. So to name these different algorithms, we are using this matrix dimension. So for Bini, we have 3, 2, and 2, and then the last number represent the multiplications for this algorithm. But more importantly, Bini's algorithm is the first one to use APA, that stands for Arbitrary Precision Approximation. And this process will introduce a tunable parameter epsilon. And this epsilon will represent the approximation error. So arithmetically, if we want the approximation error to be small, then we'll let this epsilon to be small. But on the other hand, since computer is based on floating point arithmetic, so there will always be a runoff error. But if we want the runoff error to be small, then this epsilon cannot be super small. So now we have a trade-off between these two different kind of errors, so that we can minimize the total relative error of the entire algorithm. And this table shows 12 AP algorithms, and actually there are a lot of different AP algorithms, and we are like keep looking for more, but we actually are more focusing on the practical algorithms that we can implement them on computers. And these 12 are the practical ones that we can use. And we also compute their relative errors so that on a single precision, these algorithms errors are around 1e minus 2. And this might seem pretty bad, but actually if we are using them on the neural network trainings, and these neural network are actually have tolerance, so it won't really hurt their accuracy. And we will show more testing result in the later slides. And also in this column, we compute their speed up. So these theoretical speed up can go up to 40% against the classic algorithm. And another thing I want to talk about is the parallel implementation. And here we are using the one called hybrid approach. And to show what that means, I'll use an example with Strassen algorithm on two-track machine. And the first thing we do is to do a BFS. That means we'll distribute the multiplications to different threads. And then if there are any remainder, like the M7 here, we will do a DFS. That means all the threads will work on the remaining multiplication together. And we also built a code generator. And this generator could generate the C code for any practical APA algorithms. So then with this, once we have all these C code, then we can test them on matrix multiplications and neural network trainings. So now I'll let Jack to talk about more on the result of neural network model trainings with APA algorithms.
Next, I'm going to be talking about our application of these APA algorithms into neural networks. This is a diagram of a multi-layered perceptron, which is what we use as a proof of concept for the combination of neural networks and APA algorithms. We chose an MLP because its training time is dominated by matrix multiplication. We trained this MLP on the MNIST image classification dataset. It's a very common and well-studied dataset. We use these APA algorithms in the center multiplication between these two hidden layers. The shape of this multiplication is defined by the number of nodes in the hidden layer and the batch size, or the number of training examples being passed in. We decided to keep this multiplication square, so the batch size and the number of hidden nodes were always the same, so that this was a square matrix multiplication, and so we were able to easily show how it scaled as the batch size got larger. Here are our training results. So this is a plot of the relative time of each of the algorithms we have compared to the classical implementation. So with one thread here on the left, we're able to show that with a batch size of 512, it has about 10% worse performance than the classical implementation. But as we scale the batch size up to 8,192, we're able to show that it can have up to 25% performance over the classical implementation. With 6 threads, we've showed that it can get up to a 13% improvement over the classical algorithm. And with 12 threads, it gets up to a 7% improvement over the classical algorithm. The relative performance degrades because of memory bandwidth issues, not scaling with the number of cores that we have. The best performing algorithms we have are the 442 and 444 algorithms. And this is likely because the number of multiplications that we have in these algorithms divides evenly with the number of cores that we have. We're also able to show that these APA algorithms preserve the accuracy of the network, even though they're introducing error into the system. So this is a plot of the test accuracy over the training. So this is a bit of a jumbled graph here, but what we're trying to show is that there isn't a large difference between the classical algorithm and all of these different algorithms that we have here, all of which are introducing error into the system. They're all relatively the same, and the small error introduced by these multiplications isn't having an effect on the accuracy of the network. We also wanted to show the application of these algorithms into a practical network, something with some real large multiplications that actually gets use. So this is a diagram of the VGG19 image classification model. As we can see here in this diagram, its first couple layers are convolutional, and then it has 3 fully connected layers at the end. The first multiplication that it has is a flattened out convolution. So this last convolution is flattened out to a size of 25,088. So this multiplication is, the shape of the multiplication is 25,088 by the batch size by 4,096. So this is an enormous multiplication and a place that where these APA algorithms could really improve the performance. So when we used APA algorithms in those fully connected layers, with one thread, we were able to show a 15% speed up when the batch size was 8,192. And with 6 threads, we were able to show up to a 10% speed up when the batch size was 8,192. So to summarize our contributions, we've curated these fast matrix multiplication algorithms and generated efficient multi-threaded code for each of them, with up to 25% improvement over the best classical implementations. We demonstrated that neural networks are robust to the error introduced by these APA algorithms, and we were able to improve the training performance of the VGG19 network up to 15%. Thank you for listening, and please let us know if you have any questions.